As we continue to look at fundamental identities, we need to practice. So we're going to simplify the following expressions, and we need to prove that 1 plus tangent squared of x over 1 plus cotangent squared of x equals tangent squared of x. And so if I look at this identity, I need to show that the expression on the left can be modified and simplified until it looks like the stuff on the right. So we need to get it to look like tangent squared of x, which implies that I will be working on the left side only. Left-hand side, LHS, left-hand side only. So make sure you don't mess with the right side of this identity, because we have to prove that we can make it look like the right-hand side. First thing I'm going to do is recognize that 1 plus tangent squared of x is one side of our Pythagorean identities. And same with the denominator. 1 plus cotangent squared of x is one side of a Pythagorean identity. Do you remember which ones they are? The top is secant squared of x over cosecant squared of x. If you weren't able to figure that out, that means you need more practice with your identity memorization. Secant is 1 over cosine squared x, and cosecant is 1 over sine squared of x. And so I have a fraction divided by a fraction, so to speak, which means I can flip the denominator's fraction over, and that will give me a sine squared x over cosine squared x, and hey, that looks familiar. I'm making progress. This is tangent squared x, and that's what we wanted. The two sides match, so we have shown as desired that tangent squared x is identical to 1 plus tangent squared x over 1 plus cotangent squared x. Ta-da! Notice that I did nothing to the right-hand side. Absolutely nothing to the right side of this identity. I just cannot emphasize that enough. You are not solving these. You are showing that one side can be modified to look like the other. Next, we need to prove that sine theta times the quantity cosecant theta minus sine theta is equal to cosine squared theta. Since the left-hand side looks more complicated than the right-hand side, I am going to be working on the left-hand side only. Remember, the first time you attempt these, they might not work out, and you might have to erase your work and try something else. That's why identities can be a little tricky. There's more than one way to show or prove that one side equals the other. I'm going to distribute this sine theta. Remember, cosecant of theta is equal to 1 over sine theta, which means that if I multiply sine theta in, I'm going to get a sine theta over sine theta minus sine squared theta. And again, we're trying to show that it's equivalent to cosine squared theta. So if I look at the leftmost fraction here, I can see that this is equivalent to 1. That gives me 1 minus sine squared theta. Hey, that looks familiar. That looks a heck of a lot like a Pythagorean identity. I think that's equal to cosine squared theta. Yes, it is. Because remember, and if you can't keep these straight, you just write them off to the side. Sine squared theta plus cosine squared theta equals 1. So if I solve for cosine squared theta, I'll have 1 minus sine squared theta. And so cosine squared theta is equal to 1 minus sine squared theta. And ta-da! That's what I just needed to show. And I have cosine squared theta equals cosine squared theta. And I have proven as desired, so I put a little square here. So let's just reiterate the rules. To disprove that an equation represents an identity, it's enough to find one counterexample. To prove an identity, start from the more complicated side and use algebra and the known identities to transform it to the other side. Here's another option. This is my less favorite option, and I strongly discourage it, but you will see it in your textbook. And so I have to bring it up. It's not going to give you as strong of a understanding of identities, but it's an option. So change each side separately to get the same expression. Note that all the steps you are using must be reversible. And you cannot solve the statement. You have to show or morph one side to look like the other. So for this last example, we have a statement, and we're asked to show if the given equations are identities, prove or disprove. I have a really sneaky suspicion that sine of x does not equal cosine of x. I know that if I were to sketch them, here's sine x and here's cosine of x, and they're offset by a certain amount. But there are points at which they cross. So there are points at which sine of x does equal cosine of x, but there are only 2. So if you don't luck out and find the exact place where they equal each other, you're going to show that they don't equal. So if I pick pi as a substitution, I can show that at pi, sine and cosine do not equal each other. And that's enough to disprove the claim that they're identities. So if I say let x equal pi, again, I'm not solving anything, I'm just substituting. I get sine of pi is equal to cosine of pi. Sine of pi is 0, and cosine of pi is -1. And clearly these two statements are not equal, and so the given equation is not an identity by counterexample. We could just have easily have picked 0 radians, which would have been comparing the two starting points for the sine and cosine function. We could have picked 2 pi. There are a lot of counter examples. There are way fewer actual true statements. There are actually only 2 on the period. So now let's look at the next one. We have cotangent of x plus 1 is equal to cosecant x times the quantity cosine of x plus sine of x. I'm going to choose the right-hand side to simplify, and I'll go ahead and distribute that in. I am working on the right-hand side only. So we are not messing with the left side of this identity, and we need to show that we can make it work. We could also have tried to disprove it, but I'm going to try this first. The previous one was pretty obvious. I knew what sine and cosine looked like, and I was able to just show that by counterexample that it was not an identity. This one's not so obvious. So I'm going to distribute my cosecant x to my cosine x. And I know that cosecant x is 1 over sine. So I'll have cosine of x over sine of x. Plus, remember, again, cosecant of x is 1 over sine x. So I'll have sine x over sine x. And so now I need to remember that cosine of x over sine of x is the reciprocal of tangent of x, which is the cotangent function. Plus, sine x over sine x is 1. That shows that cotangent of x plus 1 is equal to cotangent of x plus 1, and I have proven or shown as desired that the identity holds.